let's talk about integration by parts. Now, where integration by parts actually comes from, it really arises from our product rule back from Calc 1, that if we wanted to take the derivative of the product of two functions, that was going to be the derivative of the first times the second plus the first times the derivative of the second. Now, to get the integration by parts formula, what we do next is just to integrate both sides of the product rule. And so what we have there, we've got on the left side the integral of the derivative with respect to x. And then on the right-hand side, our integral distributes across the sum, so we get the integral of u prime v dx plus the integral of u v prime dx. Now, over here on the left-hand side, what we've got here is essentially the integral of the derivative, and for that, we sit back and we recall, oh, wait a minute, we've got the fundamental theorem of calculus, which tells us that those are almost inverse operations, that the integral and the derivative. They're not quite inverse operations, but they're close. And so what happens over here on the left side is we've got the integral of the derivative. Well, that ends up just being the original function. So our original u times v. Then on the right-hand side, we can write that as u prime dx just becomes v du and the integral of u dv. Now what we've done in that case is to say that du is just our usual differentials from Calc 1. That looks like u prime dx. And dv, likewise, is just going to be v prime dx. And so now what we want to do is to actually take this integral, and if we move it over to the other side, then what we actually have is our integral of our u dv is going to be equal to our u times v minus our integral of v du. And so what we have here is basically, this is our formula for integration by parts. And so this is what we'll actually put to use potentially every time that the thing that's going to trigger us to know how we're going to use this is if we see an integral of the product of two functions. And so if we see an integral of the product of two functions, then we'll know, oh, this might be a good time for us to use our integration by parts formula. All right, so let's see concretely how this might work. Let's say that somebody walks up to us on the street and says, hey, I need you to integrate this function x cosine of x dx. What can you do for me? Well, we're looking at this and we're kind of seeing immediately, well, yes, this is going to be the product of the function x and the function cosine of x. And so that's going to tell us, okay, let's do integration by parts. So if we try integration by parts, remember what that formula looks like. It looks like u times v minus the integral of v du is going to be our integral of u dv. And so the question becomes, what do we use as u and what do we use as dv? Well, let's say that we choose u equal to x and dv being the rest of our integrand cosine of x dx. So how do we get our v and our du? Well, for du, remember what that's supposed to be. It's just supposed to be the derivative of u with respect to x times dx. So we just take our derivative of x, and so we end up with du being just plain old dx. Now on the flip side, what do we do for dv? Well, we imagine that we kind of do an integral of both sides. So if we integrate the left side, integral of dv, the integral of cosine of x dx, then the left-hand side gives us just plain old v, and the right-hand side gives us sine of x for that. Okay, so now for our integration by parts formula, what happens, this is going to be equal to, so we've got, first of all, u times v. Well, u is going to be our x, and v was going to be our sine of x. So we've got u times v, which is x, sine of x, then minus the integral of our v du. So v, again, was going to be sine of x. Du was going to be dx. And so this gives us the integral of sine of x dx. Okay, so where do we go from there? Well, the integral of sine of x, now that thing is an easier integral to do. We actually know what that's going to be. We can just kind of do that immediately. So our next step is going to say that's going to be x sine of x plus the integral of negative the integral of sine just gives us cosine of x. And then we've got our plus c on the end. And so what's our final answer? Well, our final answer is just going to be our x sine of x plus cosine of x plus our arbitrary constant. Now we can take it one step further. So now if we wanted to check that and make sure that that's actually right, well, we can just take the derivative again. So if we wanted to check that the derivative of x sine of x plus cosine of x, let's see if that actually does give us x cosine of x. Well, we distribute our derivative across the sum, so we've got the derivative of x sine of x plus the derivative of cosine. Well, derivative of x sine of x, we use the product rule, which is going to give us the derivative of x, which is just going to be 1, times the sine of x, plus, now the first times the derivative of the second, well, the first times the derivative of the second of derivative of sine is going to give us cosine. Plus, now the derivative of cosine is going to give us minus sine. And so what we end up with is our sine of x plus x cosine of x minus sine of x. So our sine of x's cancel out at that point, and sure enough, what are we left with is x cosine of x, exactly what we thought that we should have. And so sure enough, that integration by parts formula does give us the right answer. But kind of one thing that we glossed over in that was we were given this integral, the integral of x cosine of x dx. And what we actually glossed over was this question that came up that said, how do we know what to choose as u and what is dv in that case? Well, how we can go about answering that question is one, just kind of by trial and error. So we did it one way. Well, what would have happened had we actually gone the other direction, that we chose u to be x and dv to be cosine of x dx? Well, what would have happened if we would have chosen u to be cosine of x and dv to be x dx? Well, if we go through the same kind of argument, and we end up saying, well, what is u? So if u is going to be cosine of x, du is just going to be the derivative of that. So the derivative of cosine gives us minus sine dx. And likewise, if dv is going to be x dx, if we integrate both sides, the integral of x just gives us 1/2 x squared. And so if we go back to our integration by parts formula, where we've got the integral of u dv is u times v minus the integral of v du, then what happens is we've got u times v, so that's going to give us a 1/2 x squared times cosine of x minus the integral of v du. So v is going to be 1/2 x squared, and du ends up being minus sine of x dx. And so what we end up having to integrate is we've got our 1/2 x squared cosine of x. A minus and a minus becomes our plus. Our integral 1/2 x squared sine of x dx. So this is one way that we know whether or not possibly we've taken a wrong turn, and that's if we look at the second integral whenever we make our choice. For the second integral, we've got a 1/2 x squared sine of x, and we kind of ask ourselves intuitively to say, is this easier? It's kind of the question that we're asking ourselves. So, did our choice make things easier? Did our choice make things easier? And in this case, we can say, well, no, absolutely it did not. That our integral of 1/2 x squared sine of x actually looks a little worse than the integral that we actually started with x cosine of x. Now, what happened in our other choice, we kind of just to put those choices kind of side by side, what happened was that we had, so if u was going to be x, dv was going to be cosine of x dx, then we ended up with our integral of x cosine of x dx was equal to x sine of x minus our integral of sine of x dx. If we made our choice of u being cosine of x and dv being x dx, what that gave us was x cosine of x dx was our 1/2 x squared cosine of x minus, or rather plus our integral of 1/2 x squared sine of x dx. And so in that case, if we look at the comparison between our two answers, or between our two second integrals, we can either integrate our sine of x up here, or we can integrate our 1/2 x squared sine of x down here. This one, the first choice, was easier to do. Second choice was harder to do. So what would probably be the correct choice in that case? Well, it's going to be to make u be x and dv to be cosine of x dx, just because things get easier to do. So that's kind of one way of looking at things, that there's no wrong thing. If you make the wrong choice and you try things and it doesn't appear to get better, then you probably know that you've made the wrong choice, and you might want to go back and try the other combination and see if you can get something different out of it. So kind of one way of looking at it is this: so I'm going to try it, see if things get better. If things don't get better, I'll go back and make another choice. Now, kind of what people have developed over time then is a little anagram that helps them to figure out how things go. And that anagram is LIATE. So LIAT. What LIAT actually stands for, the L is going to stand for logarithms. I stands for inverse functions. A stands for algebraic functions. T stands for trig functions. And E for exponential. And kind of the idea with this is that you want to choose U to be the higher in the list. So if we've got a choice between, so what we had last time, that we had our integral of x cosine of x dx. Well, if we're looking at, in this case, what we've got is an algebraic function in x and a trig function with our cosine of x. So the x gave us an algebraic function. The cosine of x gave us a trig function. So algebraic functions come before trig functions. So that was the one we were going to use as our u in that case. And so this is kind of one way of kind of looking at, well, what's going to be the best way of making those choices. So something to kind of keep in mind when you're making those choices is, I've got this LIAT device to make me remember what I should choose as u, or what might be a good choice to use as u, and what might be a good choice to use as dv. So let's see if we can put that into and practice in another example. So now let's say somebody walks up to you on the street and says, all right, I need you to integrate this function for me, x times the natural log of x dx. So right off the bat, we look at that and say, oh, hey, yes, that's going to be the product of two functions. I've got an x and I've got a natural log of x. And so I'm right back to this question of, what do I use as u, and what am I going to use as dv? And so I go over to my LIAT. So I've got LIATE. So I've got, in this case, an algebraic function in the x, and I've got a logarithm function in the natural log. And so which one is going to come higher in that list? Well, the logarithm is going to come first. And so what I actually want to do then, let's say that I want to make u be the natural log of x. And so dv then becomes the rest of my integrand. The rest of my integrand is x dx. So if I find du, that's going to be the derivative of natural log times dx. So that ends up being a 1 over x dx. The v being just the integral of both sides, so that's going to be the v being the integral of x, just looks like a 1/2 x squared. And so if I go back to my integration by parts formula, my integral of u dv is going to be u times v minus the integral of v du. So what that gives me then for my integral, so my integral of x, natural log of x dx, becomes u times v, so that becomes a 1/2 x squared natural log of x, minus the integral of v du. Well, the integral of v du becomes the integral of 1/2 x squared times du, which looks like 1 over x dx. And so my integrand in my second term simplifies. So I've got a 1/2 x squared natural log of x minus the integral of, one of my x's cancel, and I get a 1/2 x dx. And sure enough, I think that this is probably the right choice because I look at this second integral, and yes, that thing is easier to integrate than what I started with of my x natural log of x. So here I have my integral of x natural log of x dx equal to my 1/2 x squared times natural log of x minus my integral of 1/2 x dx. And so this is an easier integral to do, so I can just do that. So I get my 1/2 x squared natural log of x minus a 1/4 x squared plus my arbitrary constant from my fundamental theorem of calculus. And so here's what I think is actually going to be my answer to my integral of the integral of x times the natural log of x. And again, we can go back and check that if we want to by saying, all right, let's take the derivative of what we think the answer is. 1/4 x squared. Let's take the derivative of that, and let's see what we get. Well, the derivative of distributes across the difference. So we've got a 1/2 x squared natural log of x prime minus a 1/4 and a derivative of x squared. So the first one, we use the product rule. So we've got 1/2 times the derivative of x squared to give us 2x times the natural log of x plus 1/2 x squared times the derivative of natural log, our 1 over x, minus 1/4 times the derivative of x squared to give us our 2x. So in the first term, our 2's cancel, so we just get our x, ln of x. Our x's cancel in the second term, so we get a plus 1/2 x. Our 2's cancel in our third term to give us a minus 1/2 x. And sure enough, those in turn cancel each other out, and what are we left with? Our x times the natural log of x, exactly as we think we should have. And so sure enough, that gives us exactly what we need, and we've done our integration by parts correctly. So I hope this has kind of been a good first overview demonstration of our integration by parts, and I will see you guys next time.